Welcome to Through the Lens, a series dedicated to reveal the people behind today's breakthrough in optics. For the first season, I'll be sitting down with fellow members of the optics department of FEMTO-ST Institute in Besançon. We'll talk about their research, what motivates them, and their personal journeys. Come along as we explore the human story driving photonics forward. So today I have the pleasure to receive Dr. Luc Froehly. So you are a CNRS research scientist and the head of the opto-electronic groups in FEMTO-ST, located in Besançon. So if I have to summarize your research, I have the feeling that the main topic was application of coherent light, and we will develop it later. I saw that you did your university studies in Limoges, where you studied physics, and then you completed your PhD in Saint-Étienne, focusing on refractive index metrology in heterogeneous media. Heterogeneous media. It's not easy to say. And then you did a postdoctoral fellowship in EPFL, right? And you worked on biological imaging. And finally, you came in Besançon in 2004 to start your position at the CNRS, where you currently work, right? Is everything correct?
Everything is correct, yeah.
Okay, great. Thank you so much for coming on the podcast. We will have 3 different parts. So first, we're going to talk about your career and the motivation for going into physics. Then we're going to talk about your papers and more the science that you are working on. And finally, I would like to talk about outreach, because this is also a big part of your journey, and I found it particularly interesting. So let's start.
Yeah.
So as a start, I would like to know what drew you into physics. Was it something that you knew always, or if it is something that developed along the years?
No, in fact, my father was a scientist. He's a researcher, CNRS researcher too. So I was kind of put into the field of physics since I am a baby. So I remember he brought me to the lab in Limoges to show me lasers and interferometry and all this nice stuff that you can see in optics. And I think this was really the reason why I am in physics today.
Okay.
Yeah.
That's quite lucky.
It was quite lucky, yeah.
Coming from a family of scientists is really...
Exactly.
Okay. The next question I want to ask you is about transitioning from your doctoral work, who was more about refractive index metrology, to your postdoctoral topic, who was mostly about biological imaging. So why did you change, and what inspired this transition?
Actually, that's really, again, a kind of random process, not really random. But I was looking for postdoctoral position, and trying also to send a spontaneous candidature. And one of them was at EPFL, working on OCT and biological imaging. I had also a position in Florida, which was on a quite different topic, but finally I decided to go to EPFL. So that was really essentially due to the fact that there was a position there, and that I was interested to go at EPFL.
Yeah.
So this was the reason why I switched to this. And okay, I think my background after my PhD was kind of close anyway from what was asked during my postdoc. So that was the reason.
Okay. And do you think the position in Florida or some sort of US experience would have benefited you more, like regarding backwards?
That's a funny story, because when I came back from, because Florida really tried to hire me, so they bought me the tickets, the flights, the hotel. I was invited by the head of the lab in his house, so they tried everything so that I get there. And really, when I came back, my wife said to me, okay, really, you want to go there. But finally, looking at everything, because we were just married, and she said, okay, if we go to Florida, that will be quite hard. And also salary was not that high. So finally, it was much more easy to go to EPFL than in Florida. So she cooled me down, so that finally we decided to go to EPFL, where she was able to work too. So in Florida, it wasn't possible at all.
Okay, yes.
So yeah, and the position also, if I remember, was to begin with, was for 1 year, and at EPFL it was already for 3 years at least. So that was much more interesting on that point of view. Although I must say that coming back from Florida was kind of, really a different experience, because it's so different from Europe, and kind of you can feel already the Caribbean, or
Yes.
So that's different. So I think, but finally we went to EPFL.
Okay. And then later on, you worked on metrology and beam shaping for high aspect ratio laser ablation. So what motivates this new transition again? And how did you connect everything from your previous research?
Two different questions. First one is, again, and I think it's a bit my life. I often follow the feeling I have at a certain moment, okay? Kind of intuition that I want to go there. And for this position, in fact, what happened is that my former group, which was with Tijani Garbi, decided to go to another direction that was more biological, but no more imaging. And I was not feeling this really interesting for me. And then at that time, I had also already some contacts with François Courvoisier, which said, okay, but do you want to come in the group to work on light shaping? And I said, okay, yeah, that's fine. I would love to do that. And that's how I did that.
Mm-hmm. That's very interesting. I think it's a very important component. In the end, I have the feeling that what matters is the people you work with. And you know them and you want to work with them because they inspire you.
Exactly. I think that's really important. I remember that my father said that the most important part is that you have to find 1 or 2 people you would like to work with. And this makes a huge difference. Mm-hmm. If you are happy to work with that guy and that guys are kind of complementary of you, then everything is possible. I mean,
yes.
We had this experience with François when we began on this airy beams and stuff like that. That was crazy stuff. Because, we were all complementary and, wow, big match.
Yes, yes. And now regarding the future research, you are now an established researcher in your field. I want to ask, how do you envision the field or your research for the 5 or next 10 years? What are the challenges that you would like to solve?
The point is, as I was saying, I am not kind of typical researcher because I change a lot my research topics. And if you look at this, it sounds like it's not really connected. So I can't say that I have really a feel about that. I am more specialized in interferometry, propagation, coherent optics. That may be the general aspect of my field. But I cannot say that I am specialized in OCT, for example, or because this is something I've done at some point, but after I moved to another topics. But what is true is that things I have done in one topic are always useful in another topic. And that was often kind of a strength of mine, because often I come to another topic with idea of another one, and that make a different point of view that may be very helpful. So that's the point. So I won't say I have an idea about the future in 10 years, because maybe tomorrow some guys will come and say, okay, a very interesting topic. I think your skills may be useful for us. would you come to common results? And if it's interesting, I will say yes. So that's it. That's who I am.
Okay.
Okay.
That makes a very broad perspective, and I agree with you. I think most of the time I see that different domains of physics, typically, or even broader in science, they are studying the same topic, but with different vocabulary. And sometimes in one domain you solve some problems that could be actually applied to another one. Have you ever experienced that?
Yeah, definitely. Definitely. I mean, there are a lot of similarities often between mechanics and optics. You can find really some links, but even in optics, I mean, for example, again, these topics about when we began to work with airy beams. The point is that I was working before on geometrical optics for some other aspect, and I played with third-order aberration or stuff like that. And when I came to these airy beams, I said, "That's acoustic. I mean, that looks like acoustic." And this is how we made the connection. Say, okay, it's only acoustics. So then you can do a lot of stuff, and we did a lot of stuff that other people didn't see. Although it was very simple. So coming with another perspective always help. Yeah, definitely. Yeah.
So talking about your career in general, you have studied quite broad topic, but I had the feeling that all along what was the leitmotif was coherence of light.
Yeah.
So could you describe for people, or especially students, what is coherent light?
That's a complex topic. If we speak about books, the simplest way to speak about coherence is to say that this is the capacity of light to interfere. Okay, so it could be spatially or temporally. Okay, but basically, it's the capacity of light to be able to make interferences. That's the simplest way to say things. But behind this, there is a huge debate, there is a huge scene of the difference between a laser and a classical lamp, which can also make interferences. Although one is reputed to be coherent and the other no. So there is also this question of photon density per unit cell, spatio-temporal cell. And that's something which is slightly different. Okay, so that's something different. That makes really a difference between a laser and a thermal light. So that's kind of debate. But if we want to keep it simple, it's the capacity of a light to make interference. So this is how we define it. If you take Born-Wolf, for example, the autocorrelation function, spatial or temporal, give you the coherent length.
Yes.
So simplest way to say it.
Yeah.
But it's, I think, a bit more general than that. Otherwise, it's very difficult to difference between a laser and a classical light source which has been filtered spectrally and spatially. So there is a difference, but you cannot distinguish them only speaking about correlation. So that's the point.
Okay, I understand. So you mentioned it, like at the heart of coherent light comes lasers, and this is essentially the tool that you use on a daily basis, maybe for the applications. And among the application, we mentioned it as beam shaping and laser ablation. What are, in your opinion, the current challenge for these two topics? What is like the thing that you would like to solve in these two directions of beam shaping and laser ablation?
Probably François would have answered me better than that. But there are several challenges for the beam shaping, because you have also this always this interaction between light and matter. And this changes everything. Although you have a perfectly shaped light in intensity or also temporally, you have the interaction with matter, plasma, for example, that change everything. So you have to somehow keep this interaction in mind and try to anticipate it, so to understand perfectly this interaction, and that's really the challenge. So there is some fundamental physics there, which is pretty hard to really understand how, what is the perfect spatio-temporal shape for the light to have the better ablation you can. So that's really the challenge. I think the challenge is more in understanding this interaction and being able to characterize it than to shape the light itself, because now we have quite a lot of techniques to shape it spatially and temporally. But the interaction is still a big challenge that's it's quite complex to compute, needs a lot of power of computation, and also understanding of what's happening. So that's, I think, the main challenge.
Okay.
More a question of interaction than a question of optical shaping, I guess.
I see.
This is my feeling.
Can you give for the broad audience some application that everybody could understand about these two fields of research, laser shaping and laser ablation? Yeah,
definitely. If you think simply about micromechanics and, for example, watch fabrication, you need very small gears, and sometimes with quite hard or the stiffness of these materials are quite hard. So it's pretty difficult to shape them. And for that, you have to use tools that needs to be very precise, and also to be able to, you need both high precision of the cutting, and also you need something which is able to ablate diamond as well as other materials, which are pretty stiff. So laser is perfect for that, and especially femto lasers. And this is why it's interesting to shape the light, because, for example, if you think about a gear, in general, in mechanics, right angles are not good at all. So you need to make kind of rounded borders. And that's pretty hard with classical methods. If you can do, let's say, round cuts round cuts, then it's easier. This is what we did with lasers when we did these airy beams. It's kind of round surface that enables you to profile directly your materials, even if it's pretty stiff. So that was an possible application for that.
Okay. Very interesting.
And it's also, if you think about these Bessel beams, which are long needles, that's very nice because you can really drill holes, long holes in one. So that's really interesting.
Yeah.
But you cannot do it with a classical beam.
Yes, I have seen those results, and they are particularly impressive. Because of the depth and the damage is almost nothing. Yeah. It's very cool. It's edge-cutting science.
Yeah, because it's really interesting with Bessel beams that you can decouple the lateral resolution and the depth of your Bessel beam.
Yeah.
So that's the point. Yeah.
So right now we talked a lot about experimental work, but I know that you have strong experience in optical simulation, and notably with the Optic Studio, who was formerly ZMAX. I want to know how essential are the simulation in your work, and what are the limitations or things that are still unresolved?
Yeah, that's also a nice point, because I came to Optic Studio by error again. No, in fact, I discovered that when I was at EPFL during my postdoc, but then I let it for a while because I'm more an experimentalist guy at the beginning. But I experienced some trouble in the lab with some water on my experiments And that crashed everything, so that during that time, it took some time to get back to have some materials, and it happened me twice. So during that time, I say, okay, I have to spend the time to do something else. And then I came back to Optic Studio and discovered that it was a big benefit to help to predict how build up good to improve our Bessel beams experiment, for example, because we use a lot of components, imaging components, with high numerical aperture, so you add a lot of aberrations. And this helps really to predict what you will really get at the end. So before buying very expensive microscope objective, you can just say, okay, that makes sense to buy it or not. So that's how I began with that. And then from experience to experience, I use it more, discover that I can use it for also optimizing setups with Bessel beams, stuff like that. So finally, I'm using 90% of my time now is trying to do simulations about using this kind of software. Because it's quite complex, it's quite powerful. You just have to know how to use it and what are the limitations of this system, because it's basically a ray optic system.
Yeah.
So you have to be careful if you want to. Bessel beams are not at all ray optics, or depend, but you can still use it. So you have to trick it to find out, and that's what is funny and kind of research there. It's how to use this complex stuff to do things that we want to do. Mm-hmm. Yeah, that's a bit of stuff.
And you mentioned limitation. Can you name one, for example, where you...
Yeah, the big limitation is that it's a ray optic system. So if you want to deal with propagations, coherent propagation, then it's not done for that. As soon as you are speaking of ballistic behavior of light, then it's fine. But if you want to add some propagation inside of the wave nature of light, then you have to be really careful. You can use it at some point, but you have to be careful.
Okay.
And that's what I would advise is it's often better to come from experiments to do simulations at the reverse. Because if you did some experiment before, you know that there are limitations and you have to be careful to what you get. So you have to have an idea of what you should get before doing simulation.
Okay.
Yeah.
Yeah, that's an interesting point of view. I was always thinking about the reverse, actually. The simulation will give you, let's say, broad limits about your experiment, and then you realize that your experiment is even
maybe you can see the reverse,
yes.
But from an experimentalist point of view,
yes.
It helps to constrain your system and say, okay, this has no sense.
Yeah.
I made a mistake.
You mentioned 90% of your work is now simulation, but before you were turned more into experimental work. Do you miss it?
Yes, somehow yes. I kind of try to do some experiment in my simulations, but it's not the same. So yeah, definitely I still hope that I will be able to do some more experiments, because that's really where I developed also some feeling in some parts. So that was really wonderful to think about something and to begin to see what's happened when you try to do it. And that's really something I miss a bit still.
Yeah, it feels maybe more concrete to build something. It's actually kind of you have a Lego set in front of you.
At some point, simulations are nice, but this is to do something.
Yeah.
And then this is concrete. And there are also some constraints that you didn't predict it by simulation. So you see the real life when you go to that. And really, yeah.
Okay.
Yeah.
So that concludes the science questions that I had for you. And the last part of the discussion I want to have with you is about outreach, as I mentioned earlier. And so can you tell me more about this? For example, describe one of or multiple outreach activity that you're doing and why they matter to you.
Really began with the Year of Light. And then I discovered that was something very, very nice. I really loved to do that, trying to explain physical behaviors like holography, for example, to very broadband people, and that was really interesting because I also experienced that when I try to teach, that often trying to explain helps you to understand what you're saying. And sometimes we science is not something which is for only a few people. That's for everybody. And everybody can understand science.
Yep.
So this is something which is important to me, to try to share this with people and say, no, you can understand that. We are not different from you. We are not elite or whatever you want. You can understand that. And I will try to make you understand that. That's something important to me.
Yes. So actually you mentioned 2 points that are linked to my 2 questions I wanted to ask you. So perfect transition. So first of all, how do you explain such complex topics? Like, laser, everybody know, but it's actually complex physics behind. And if you think about the application or the beam shaping or all the application or the research we have, how do you translate this to non-specialists or even kids?
First, you need to do it not only once. It's with repetition, having different kind of peoples, that you develop skills, saying, okay, this doesn't work with this kind of people, maybe I can use another way to see it. And this is how finally you find your own rules to say, okay, if I want to explain holography, then I have my tricks. And then this, I know it will work with them, and that's it. But
okay.
It needs to...
iterate?
Yeah, to iterate, exactly. That's a kind of iteration process, exactly. First time, it's rare that it works.
Yeah.
You need some experience on that, and because you see what doesn't work, why people don't understand that or not, or understand what is clear, what is not clear. You have to somehow find examples in their life. That's what's most clear, or something that they can see, and that helps a lot.
Yeah. And you mentioned also scientists are not elite. Everybody could do science. Where do you think this idea that science is only accessible to a few is coming from?
Society. Often when you speak with people, family, or different people, they say, oh, but you're doing science, you have a PhD, your brain is like this. No, not this feeling. And I think it's essentially come from society, maybe a bit from our own medium, maybe also. But I think essentially society seems too complex, but it's not.
Yes.
It shouldn't be, at least.
If you find the right teacher that match the way that you can understand to match the way that you can understand, it makes it much easier, I think.
Yeah, sure.
Pedagogy is central in our work. And I wanted to say something else. So, looking ahead, is there any outreach activity that you would like to develop, or a goal that you would set for yourself in this direction of, let's say, vulgarizing science?
We have a very concrete, which will come soon, activity, and that's something that was in my mind for already a time. We will soon go to the Maison d'Arrêt de Besançon.
Okay. Is it like a prison?
Yep. But
Okay.
it's not exactly a prison. The Maison d'Arrêt is a place where all people that have been arrested comes before they are judged.
Okay.
So it could be from, can be very different cases. And this is a place where they wait until they are judged and
Okay.
go to some prison. Okay. And we will try to make some scientific activities there. And actually this exists in Besançon since a long time. We discovered that recently. And there is each month some visitors in prison that bring some scientific thema for 1 hour or more, 1 hour and a half. And that's something we will do next year.
So what kind of activity do you plan? Is it more technical? You bring material?
The point is that you cannot bring a lot in prison, you know? This is quite constrained. Yeah. So we will see. We will see. Depends also from one place to another. In Marseille, I think they were able to bring a bit more. We'll see what is feasible there. They are not used to bring a lot. It's even difficult to come with you cannot come with your laptop. Mm-hmm. So we'll see. That's still a surprise. We'll see.
Okay.
Coming soon.
Yeah. So I want to conclude with why we are making the podcast. So I want to know if you have any advices for students that are considering a degree in physics or in optics. And especially, okay, let's start with this. Yes.
Main advice is, and I've always given the same advice, is to be curious of everything, to not to be afraid to do not understand things, but really to dig and try to understand things. And I think in this field there is still quite a degree of freedom, freedom to sing, freedom to dig a subject, although it's a bit more constrained than it was, but still it's a place where you can practice a kind of freedom of thinking. Yeah.
Yes.
Yeah.
And photonics.
But you have to be curious.
Yes.
Yeah.
Yeah. And so photonics has seen quite some increase in terms of investment in the last years as well. So hopefully it will also come with job creations.
Hopefully.
Yeah.
We'll see.
Yeah. And okay, my last question is around you, about your colleagues. What qualities differentiate a good researcher, or like what do you need to have to be successful in this field?
That's a different question. Successful, or I think it's kind of
fair.
Yeah, I think there are different profiles, and we have to keep in mind that there are different profiles, and we need all these profiles to make a good team.
Yes,
I think that's maybe a drawback of our system in France, but elsewhere too. It's often we associate science to some people that are enlightened, Nobel Prize, for example, and sometimes we forget that there is a bunch of people around them that have helped them to go there, and without these people they cannot, because you need these complementarities of profile. And of course, there are some of them which are much more the guys who has the idea. The other one is the guy which has the technical idea, the way to do it. The other one has the intuition of that. And the other one is able to see in a big equation how physics works. So, I mean, you need all these guys. And also technician, and also you need a lot of people to do good research. I mean, so success is a kind of tricky word. I mean,
yes.
If you think about the success, Nobel Prize may be a success. So this is very different to be success in your life, in your career. Probably there are several ways of seeing it. So I won't be able to answer it correctly. I mean, what is sure is that you need a lot of people around you that you would like to work with and that you are happy to work with. And there could be a common success. That's the point. You really need these complementarities of people, of profiles, to be able to do something which globally will add something to the society, add something to the science. That's maybe how I can see the success. It's more this way.
That's very nice, actually. A very nice way to conclude our interview today. So thank you very much for all the interesting things we talked about. We saw both aspects of science, simulation, experimentation, and also outreach, where you have a big part as well. It was a pleasure to discuss with you.
That was a pleasure too.
And so, thank you again.
Thank you, Mathilde.